All right, well, hello, grade 12s. Yeah, listen, textbook help. My pleasure. Okay, I'm going to give you that right now. All right, so these questions here on page number 219, I think. Okay, I've got the first few questions here. Let's start with number 10. It says a bungee jumper. I know you're concerned. I cleared my throat. It's not COVID-19. See, we got tested. Well, my wife got tested, and if she's negative, we're all negative. So, all right, number 10. A bungee jumper, okay, is standing on a platform 48 meters above a river. The length of the unstretched spring is 10.1 meters. The force constant is 65.5 newtons per meter. The jumper falls from rest and just touches the water at a speed of 0. All right. So the thing about this problem that I'm not 100% sure about when I read it is what happens. Does he fall 10.1 meters with a slack string, or whatever? And then, okay, so what I'm wondering is what the stretch in the spring would be, okay, when he reaches the bottom. Would it be 48 meters or would it be 37.9 meters, okay, if you follow me here? And so I'm not 100% sure what they mean in the question, okay, but let me just read it here again. So look, a bungee jumper of mass, that's the mass, okay, that's fine, is standing on a platform, and the platform is 48 meters above the river, so that's your height, your change in height. The length of the unstretched bungee cord is 10.1 meters. Now, usually when you jump on a bungee cord, the bungee cord is kind of gathered up behind you. It's not hanging down from somewhere higher. And so I'm going to go with that. It could be in error. We'll see what the answer in the book is. But all right, so let's go ahead and do it. So I'm going to assume that guy is standing on a bungee platform. Okay, and here's the bungee cord, all coiled up or whatever, and that is attached to the guy. Okay, or whatever. And then he jumps over the side of this platform, okay, like that. And then the spring uncoils, and then he ends up with this stretched out bungee cord like that, and of course he ends up down here, like something like this, right? So there's the guy, again, his bungee cord. Anyway, that's the bungee ride. So I'm going to assume it's kind of like this. So at the top, we'll make our little list. We have EG, EK, and ES, right? Those are the 3 types of mechanical energy. And this is one of those things, the guy's dropped, right? So you got to think of energy when you think of that. Now what the question says is, we know that this is the height, the distance all the way down to the water is 48 meters. Now I'm gonna erase this line at the bottom, if it'll let me. Okay, so I'm gonna erase that line at the bottom. He doesn't quite go down to the bottom now as I read it here. All right, so he's 48 meters above the river. The length of the unstretched spring and the bungee cord is 10.1 meters. The force constant is 65.5 newtons per meter at a height of 12 meters above the water. So it's 48 meters all the way down, but he ends up 12.5 meters above the water line. All right, so I'm just trying to get my data straight here. You don't have to draw a diagram to do these, but sometimes it helps, right? Like it's just sort of a little guide. All right, now here again, EG, EK, and ES, right? 3 types of energy. All right, so what do you have at the top? Well, we definitely have gravitational potential up there. EK, though, is 0 because the speed equals 0 at the top because he just drops himself over the side. The spring energy is also 0 at the top, okay, because it's not stretched. So in other words, X equals 0 at the top. There is no stretch in the spring, okay? Now here at 12.5 meters above the water line, if you want, you can think of it then, he therefore still has EG because he could go lower, okay? We're going to assume that he could still be moving. It's not at its maximum stretch. It could be moving down, so there's going to be some speed. Or wait, did I read that question right? Yes. So when he touches, he can touch the water. So if he fell the full 48 meters, the speed would be 0. But here at 12.5 meters, the speed is definitely not 0 there. So down here, the speed is 0, but not here. Here he's going to be moving downwards still, okay, with some velocity. All right, and then your spring energy, you definitely have some of that. And your x value is going to equal, well, you've fallen, okay, so he fell 48 meters, but it didn't start to stretch until 10 point, or sorry, he fell, what was it, 37 point, 12 point, am I getting these numbers right? Yeah. Okay, here, so let me just do the math quickly, because I'm tired and it's a bit lazy here. So it's 48 minus 12.5 is 35.5 minus 10.1. So the stretch is going to be 25.4 meters. Now I got that by subtracting 48 minus 12.5, and then I subtracted another 10.1 because it said that the natural length was 10.1. So in other words, it's just going to start to stretch once he's past the 10.1 meter mark. So this distance would be x from here, okay, the stretch after that. Now I'm assuming, okay, that that's what they mean, okay, with these bungee rides. All right, so now we just go ahead and do it. What are they asking? All right, so we're going to need to figure out the k. Oh no, the k value is given. So we got the k value, we got the x value. That's okay. Yeah. So anyway, let's just put it in. Let's just put it in and see what happens. Okay. They're asking us, I think, for the speed, right? Yeah. What is the jumper's speed at a height of 12.5 meters? I'm just reading this first time. Okay. So, all right. So it goes like this. You would go mgh. So the top has to equal the bottom, or the top has to equal the at 12.5 meter mark, okay? So this mark here, the top has to equal that. So therefore, mg times 48 would have to equal mg times, so that's the eg at the top, so mg times 12.5, right? Plus 1/2 mv squared is the ek, plus half kx squared. Now, if I'm right, I think the only thing that's unknown in that whole equation is v. I think we've got everything else, right? Yeah, so the mass is 64.5, pardon me, 64.5 kilograms. K is 65.5 Newton per meter. And so, oh, and we've got the stretch. The stretch we said was 25.4. Okay. And then, yeah, that's it. So you've got everything, just solve it for speed. Done. Okay, so that's your energy approach. So you're always looking at the total energy being conserved. And so you just got to organize yourself. So this is at the top. This is at the 12.5 meter mark. And the total energy would have to stay conserved the entire time, right? And so the energy at the top is just gravitational potential. So this is Eg at the top, right? This is Eg at 12.5 plus Ek at 12.5 plus the spring energy at 12.5. Now, I'm thinking that x is 25.4. If the spring was ready to stretch as soon as he jumped, that would make the x value a different number. So like if, in other words, the spring was suspended from up here somewhere and it was like already just hanging unstretched, then what happens is it would start to stretch immediately. and that would make his x value, just in case, I'm just telling you that in case I've interpreted it wrong, the information in this question, that would make the x value 35.5. So it could be, but then why are they telling us 10.1 meters? I'm thinking I did it right. Okay, but there's a chance that x could be 35.5, but I think I did it right. So I would just go with what I wrote here. All right, so that's how you do question 10. Good one. I like that one. Okay. All right, number 11. A toy car is attached to a horizontal spring. A force of 8.6 newtons causes the springs to stretch 9.4 centimeters. All right, so 11a. Guys, really? Seriously? Asking me this question? F equals kx. Force on the spring is kx. They tell you what you're looking for is k. They tell you that x is 0.94 meters. Convert that to meters, right? And they tell you that the force on the spring is 8.6. What's wrong with me? 8.6 newtons, of course. And that's it. Okay. So now that you got that, 11a, no problem. Okay. Now, it says, what is the maximum energy of the toy spring system? That question B. They just want you to say this. What's 1/2 kx squared? In other words, if you only compressed it, you did this work to compress it with a force of 8.6 newtons. And then what happens is that creates a certain amount of energy in the system because you did that. And that's the maximum energy in the system at this moment. Okay? So just plug in the numbers from above. Same k, same x. Okay, and that's it. All right, number 12. The maximum amplitude of vibration that a human eardrum can withstand is 1 × 10⁻⁷ meters. Wow, that's kind of small. It's a tenth of a micron. Okay, and if the energy stored in the eardrum membrane is 1 × 10⁻13 joules, what is the force constant of the eardrum? Are you seriously asking me this question, guys? All right, again, this is an energy one, so you're going to go ES equals 1/2 kx squared, right? What are they looking for? The force constant again? Yeah. So K will equal to ES divided by x squared. Okay, just solving for K algebraically. Now what they tell you is they give you the number of joules. So you just, guys, just plug the numbers in. Okay, it's all good. It's already in meters and in joules, so you're good. All right, number 13. Okay, a 22 kilogram cart slides down from rest at a ramp angled at this, blah, blah, blah. There's the spring. I mean, the picture says it all, right? Okay, the spring is compressed a distance of 0.3 meters before, pardon me, the crate stops. Determine the total distance the crate slides along the ramp. Friction is negligible. All right, let's just go with this picture here. So again, this is an energy problem, not a force problem. It's dropped. Okay, in other words, it slides from rest and it's just sliding down. So what kind of energy does it have up here? Well, Eg, Es, Ek. All right, so this is not even touching the spring yet. So let's get rid of that one. Okay, X is 0 after all. There's nothing touching the spring. Here it's from rest, so V is 0, so there's no Ek. So once again, the only energy at the top, Eg. Now, when it squeezes down here, let's say it ends up here like this, it's going to compress it, so now it's a shorter spring or whatever. At the bottom, you've got, let's make our list again, Eg, Es, and Ek, 3 types of energy, right? Again, it's going to come to rest at the bottom, okay? Like at its maximum compression, okay? And it says that it stops. Now, here's the key though. It stops, but it's not in equilibrium, okay? So it's not going to stay stopped. It's going to bounce back up like anything you drop onto a spring. That's what happens, okay? So it's not in equilibrium, but the velocity for a moment is 0. Now, of course, you do have spring energy because it's compressed. And because it's as low as it's going to go, you don't have any of that. So those two are gone. And so we're going to do this. Let me just do this question right here. You're going to say, here's the top. here's the bottom, right, of the motion. And so you're going to say that the top equals the bottom. And we've got mgh will equal half kx squared. But there is a trick to this question. You have to be careful about what h is equal to. Okay? So look, h, if it slides down to here, okay, or whatever, then h is that, right? Okay. Now let's say he slides down a certain distance here. The spring is compressed a distance of 0.3 meters. Okay, that's what it says. So we already know what x is, by the way. X is 0.3 meters. It says it right there. Okay. It says determine the total distance the crate slides along the thing. Okay, so let's say this is the distance, call it d, before it touches the spring, but it's also going to slide x, right? Like that. Okay. So now the thing is that this makes a right angle triangle. Here, actually, I'm going to include x in there. Pardon me. I know I'm being annoying. I didn't really think it through ahead of time. But look, so this distance includes x. Okay, just bear with me for a second. So that distance includes x. So it's going to slide a certain distance down there, right? Okay, all the way down to there, and then your little x values in there. But I don't want to confuse you. We're going to count the entire thing as d, the distance. There's a little right angle triangle here. Okay, and this is sort of the secret to the question. You've got d, you've got h, and then you got this side here, and we know that this is 29 degrees. And so what we're going to do is we're going to say h is equal to d times the sine of 29. Okay. So, therefore, okay, you're going to go like this. mg, so now we proceed down here. mg times h, which is d sine 29, has to equal 1/2 k times 0.3 squared. Now they tell us what k is, 890. And so you're going to get, what's the mass? 22 kilograms. All right, so they tell us that 22 times 9.8 times d times the sine of 29 would have to equal half of, what is it? 890 times 0.3 squared. All right, and then d is your answer. That's it. So I thought we were going to have to separate x and d, but you don't have to in this question, so that would just make it more confusing. I don't want to confuse you. You got enough problems, right? So there you go. So that's how you do number 13. Okay, now there was a number 14, so just let me pull that up for you. Number 14, just a moment. Okay, just let me bring that into this document. All right, there's number 14. Okay, so a ball is attached to a vertical spring with force constant 28 newtons per meter, released from rest from the unstretched equilibrium position of the string. Determine how far the ball falls under negligible air resistance before being brought to a momentary stop by the spring. Yeah, I mean, you're dropping it, right? So here's your spring. Here's your ball. Okay? And what's happening is it's not stretched, okay, at all. Like it's just, so x equals 0 here. So again, we'll go EG, ES, and EK. So at the top, surprise, surprise, those two are 0 because x is 0 at the top and V is 0 at the top because it's dropped from rest. Okay? Now, so you only have one kind of energy at the top, gravitational potential. Now this thing slides down, or not slides down, falls down, more precisely. And it falls down, and down here, what kind of energy do we have? Well, it momentarily comes to rest. So again, EG, ES, EK, what do we have? Well, we have none of this left because it's not going to go any lower. We have none of that because the speed is 0. And we got this one though. Okay, so once again, top equals bottom. So mgh at the top will equal half kx squared at the bottom. Just go ahead and solve. Okay, I think they give you all the numbers. 0.2. Oh, x and h and x will be the same number. Okay, so 0.2 times 9.8, because this will be the stretch. That's your height. That's also your stretch. Okay, so 0.2 times 9.8 times x equals 1/2 k times x squared. That will cancel with that one. Solve for x. You get x equals 2 times 0.2 times 9.8 divided by k. Okay, and that's how you do that one. All right, just like that. It's all done. Okay, so I hope that helps. And yeah, if you need anything else, just let me know.